Okay, so for this one we need to prove that there is a positive integer that can be written as the sum of 4 perfect squares, but not as the sum of 3 perfect squares. And the squares could be repeating, so they don't have to be distinct. So for this one, proof, notice that. Now this is a constructive proof that there is such a number. Now we will construct such number, 7. 7 is equal to 4 plus 1 plus 1 plus 1. The sum of 4 perfect squares. However, it's impossible for 7 to be written as the sum of 3 perfect squares. Why not? The reason this can't happen is if you have 3 perfect squares, if I use a number 9 or higher, then I would get a sum that's bigger than 7. So the perfect squares that I choose, if I have 3 perfect squares, must be either 1 or 4. Also, if I choose only 3 of these numbers, I can't make any combinations of 1 and 4 using only 3 of them to get 7. Okay. Let me write that out in more detail, but that's basically the essence of the proof. This happens because we must choose 0 and 4 as the perfect squares. Or else the sum would be larger than 9. And, well, if I take 3 1s, that's equal to 3. If I take 2 1s and a 4, that's equal to 6. If I take 2 4s and a 1, that's equal to 9. And if I take 3 4s, I get 12. So 7 can be written as the sum of 4 perfect squares, but it cannot be written as the sum of 3 perfect squares. And so that's the end of the theorem. It turns out that this actually is a theorem that every positive integer can be written as the sum of 4 perfect squares or less. That's called, I believe, Waring's theorem. We're not going to be proving that here, but this is just to let you know that this is actually an illustration of something that's a theorem from number theory that's actually a little bit more complicated than what we're dealing with in this course.